So this is the second module, and we come to basically the classic topic of uh, galaxies. So as I already mentioned to you at the beginning, that in 1920s, it's only like about 100 years ago that we figured out that there are other island universes like our own Milky Way galaxy. Uh, and the key advance that allowed us to do so was ability to measure the distances to these nebulae, which essentially looked all, in a lot of their respects, very similar to each other. And it turns out some of those nebulae are actually as small things as dying stars, planetary nebulae, and some of them are island universes, like our own Milky Way far away. So after Hubble figured out that there are island universes, the next natural task was to actually go look for them, classify them, how do they look like. So this is what, so Hubble had access to this, the largest telescope in the world at the time on Mount Wilson, and they sort of made catalogs of nearby galaxies, classified them according to their appearance. So this classic classification of galaxies according to their appearance is called morphological classification of galaxies. Basically, you look at the appearance, morphology of the galaxy and try to classify them. This is sort of a modern version of Hubble's classification, and this is called Hubble's tuning fork. And as you can actually see, it's sort of drawn in form of a tuning fork. In fact, earlier people thought that this was some sort of an evolutionary sequence, like the H.R. Hertzsprung-Russell diagram of stars, which is some sort of an evolutionary sequence, that that stars live on the main sequence and they evolve off along certain trajectories and so on. But turns out that's not quite correct. This is not an evolutionary sequence, and yet this sort of tradition is used. So the galaxies don't evolve along it or something like that. So so there are elliptical galaxies, which are sort of they are featureless. They appear like ellipses, and they can be as as round as a sphere or a circle to a pretty flattened ellipses. And then this E0 and S0 may look the same to you, but they are actually not. Here are actually real examples of real galaxies which are of these classes. Okay, so E0, so this number after E stands for this is basically 10 times 1 minus B by A. Basically, B and A are the semi-major and semi-minor axis. So their ratio 1 minus of that times 10 is here. So if this number is big, that means the ratio of the two is bigger. I mean, it's just a very simple exercise. Okay. The other thing that you see here are that these galaxies are actually like diffuse clouds rather than point-like stars. Okay. So that's why they were quite mysterious objects at the beginning. Okay. So what's the difference between E0 and S0 galaxies? The S0 galaxy not only has this spherical part, but it also has a disky component. So here is an image of an S0 galaxy, right? You see the inner part, which is sort of spherical, which almost looks like an E0 galaxy, but outside it is a diffuse component, which is like a disk. Okay, so that's why it's an S0 galaxy, distinct from an E0 galaxy. So these are elliptical galaxies, and on the right, what we have are spiral galaxies.
S0 is a lenticular galaxy.
S0 is something called a lenticular galaxy. it has a central part which is like an elliptical galaxy, and an extended part which is disky but does not have prominent, it does not have spiral arms. Basically, that's the difference. The most massive galaxies in the universe are of this kind, S0s, and a lot of them sit at the centers of galaxy clusters. Okay, so galaxy clusters are very dense places in the universe, and places where a lot of mergers between galaxies happen, because that's where overdensity of galaxies is. Okay, and as you move towards the right, uh, the galaxies become more and more dominated by spiral arms. Okay, and the top and bottom are distinguished by the presence of something called a bar. Okay, here in the bottom part of this tuning fork, there is this feature, a linear feature, which is called a bar. And on the top, you have these spiral arms. As you move towards the right, you become more and more dominated by the spiral features. A larger fraction of light is coming from the spiral features. Okay. And the same is true for here. The spirals become more open as you go towards the right. And the central part, this like bulge part, so there is a bar, for example, here, there's a bar, there is a bulge, and then there are spiral arms. Okay, the spirals become more open as you go towards the right, and they are more dominated by spiral arms than the central bulge. Okay. Okay, so so the galaxies are composed of stars, but why do we not see them as stars? Why do we not see, like, at every place there is an extremely bright object and then nothing, and then extremely bright object and then nothing, right? That's what you expect. Why do we not see that? Can someone quickly tell? I have actually mentioned this previously in the class. Right, so basically the point is, the star is so tiny that you cannot resolve stars individually. So the light of the star that you're getting gets smeared out on the sky. If you have atmosphere, it gets smeared out over a larger angle. And this phenomenon of smearing out of point sources by the atmosphere is something called seeing, or atmospheric seeing. So you may hear about things like, oh, seeing in Ladakh is these many arc seconds, or seeing at mountain tops is much better at compared to seeing at the ground or the sea level. So what it means is that this spreading out in angle of point sources is much less as you go much above into the Earth's atmosphere. Okay. So what's the rough, like, what's an order of magnitude distance, mean distance between stars? No. Not the size of the galaxy. This mean distance between stars. Yeah, light years or parsecs. So, and if you put, so the nearest big galaxy is Andromeda, which is at a megaparsec away, or 500, 700 kiloparsecs away. So if you put 1 parsec at a distance of a megaparsec, what is the angle between two stars? In Andromeda, for example, it's 10 to the minus 6 radians, right? So that would correspond to how many arc seconds? 0.2 arc seconds, right? This is 10 to the minus 6 radians converted into arc seconds. That is multiplied by 180, 3600, and divided by pi. Pi radians is 180 degrees. 1 degree has 60 arc minutes, and every degree has 60. Every minute has 60 arc seconds. This everyone has to know. If you don't know it, just this is the time. if you are doing any astronomy, all these like beginners things you should really be very familiar with. Okay. So the point is, the stars in Andromeda are basically smeared out. So, smearing, like say, seeing on the ground in normal conditions is like an arcsecond or worse, whereas the distance between stars in Andromeda is 0.2 arcseconds. So all these individual stars in Andromeda are basically, smoothed out over an angle which is bigger than their separation on the sky. That's why it appears like a milky appearance, like a spread out appearance instead of like individual stars. Okay. Most of the volume also in a galaxy is empty, right? Stars are extremely small, right? The sun, the radius of the sun, how much is roughly the radius of the sun? Right, so 7 times 10 to the 10 centimeters. Compare it to the distance between stars, which is a parsec, right? So 10 to the 11 centimeter divided by 3 times 10 to the 18 centimeters. So like 10 to the minus 8, 10 to the 8 orders. So most of the volume in a galaxy is empty. And the probability of having 2 stars in the same line is extremely tiny as well because of this. There are a lot of stars, but the area of a star is tiny. So basically, when you're seeing the light from the star, you're seeing essentially all of it because none of them are like blocking each other. So basically, galaxies are transparent, right? You see all the light emitted by the galaxy. It's not as if you arrange all the stars in a single line and you're hiding the stars which are behind the front star. That chance for that is extremely small. Okay, so this is an extremely important concept that you should be totally familiar with. Cool. So, which ones, which galaxies are more common? If you just take a sample of nearby galaxies, which ones do you think are more common, spirals or ellipticals? Spirals are more common. So it's sort of roughly like 70% spirals, 30% that their abundance is. Which are the most massive galaxies? Are they so if you take the most massive galaxies in the universe, would most of them be spirals or ellipticals? Yes, so elliptical galaxies are more massive in general, but it's not like all elliptical galaxies will be massive than spirals. There's like a distribution of masses. Massive in terms of mass, not in terms of radius is a different thing. Radius is size, right? So mass and size are quite different. The elliptical galaxies are actually quite compact. Their sizes are not as big. They're not as diffuse. Okay.
Recently, there have been certain studies that show that at the center of the biggest clusters, there are more and more spiral galaxies present as compared to ellipticals.
Towards center?
The PGGs of the biggest clusters.
Brightest group galaxies. Of biggest clusters are?
Like as in, they are the most massive galaxies.
That is correct. So yeah, S0s, as I said, are not quite spirals. They're disk plus, yeah. So these are the most massive. So these are like a composite of a disk, which is outside, and a bulge component. So a lot of most of the galaxies have bulges at their centers. And these bulges you can actually think of like mini elliptical galaxies at the centers of disks or spirals, right? And the bulge plays a very important role because there's all this correlation between the black hole mass and the bulge mass. There's a lot of correlations between galaxies, their luminosity, their sizes, and so on. Okay. So this is one way of looking at the classic way. this sort of subject has been studied a lot, starting from Hubble uh, to people like devoculars and so on, these like standard names that you would encounter when you study galaxies. And there have been like various ways of doing this morphological classification, because this is essentially, this is like, look at this image, where would you put it among these three or whatever n classes? This is the simplest thing that you can do. The first thing you have to do is classify them, and then you try to get to the physics of it. Which of these do you think are younger systems? These guys or these guys? Spirals. Spirals are younger, and which of them are blue? When I say younger, bluer, things like that, that's not the definition. Definition is morphological. So if you had a red galaxy with spiral arms, you would still call it spiral, because the classification is morphological. But the chances of a spiral galaxy being red that is dominated by old stars is small. I mean, now with these surveys of galaxies becoming so like deep, they are able to find all sorts of exceptions to these rules, but they are smaller classes. What we are talking about here is like the majority, like 90 some percent follow what we are saying here, but not all of them. Okay. So most ellipticals are red and dead. What does that mean? Red and dead galaxy. They are formed out of old stars. So so young stars are bluer, more massive, and short-lived. So the fact that they are blue, most of the time spiral galaxies are blue, what it means is they're forming stars now. Because you still see these stars which have an age of, which have a lifetime of 10 million years, you're still seeing them. That means they have formed stars within last 10 million years. Okay, so this is another way of looking at the same thing, rather than in form of that tuning fork that we just encountered. So here, this is that S0 galaxy, the disk plus bulge system, which is the biggest. So here, the arrangement is increasing bulge mass, and towards the right as you go, you have more open spirals, like the spiral arms become more and more open rather than being tight. And these systems are more gas rich. Gas is what's required to form stars, right? And if a galaxy is forming stars now, that galaxy must have gas from where these stars came out. Okay. So this is another way of looking at it. Sometimes this S0 at the centers of galaxies is also called CD galaxy, central dominant galaxy. Right. So which of these galaxies do you think would have most massive black holes? So you know that most galaxies in the universe have black holes at their centers. So I don't know, let's see how much do you know about astronomy. Which of these galaxies do you think will host most massive black holes in the universe? So let me also give you the hint that these elliptical galaxies, massive galaxies, are thought to form from mergers of galaxies. Okay. So yeah, now which galaxies do you think are more likely to host most massive black holes, supermassive black holes at their centers? These guys or these guys? Elliptical is fine, but here or here on top. Yes. CD galaxy, for example, will have the most massive black hole. So there is this black hole mass bulge mass relation, that the supermassive black hole mass is actually proportional to the bulge mass. So the bigger, the more massive the bulge, the bigger the black hole. All these are statistical statements. You can find exceptions, but most of these guys satisfy these tight relations. the fact that these relations are so tight means that the process of evolution of galaxies and black holes are tightly, intimately connected, right? Otherwise, why would you have such tight relations, right?
So,
Yeah.
spirals, do the black holes govern the spiral arms, the shape of the spiral arms?
Absolutely not. The black holes do not, their sphere of influence, that is, the gravity dominates very, very locally. So the spiral arms and so on are due to self-gravity and shearing and all that. The black hole has no direct role in spiral arms. Okay. Okay. So yeah, so when you read that textbook portions, you'll actually learn a lot of facts about these things. So I've actually made my little notes, but let's see. Some of those things I've actually mentioned. Uh, which galaxies, spirals or ellipticals, should have dust, more dust, fraction in terms of a fraction? Why? Cold gas, dust go together. Right? Dense gas, molecular hydrogen, CO emitting gas, forms where you have dust. That's right. So ellipticals are smooth, round, no dust lanes, no spirals. Okay, even in ellipticals, there is like there are subclasses in all these. Okay, so there are these CD galaxies, which are like composite, and then there are giant elliptical galaxies. The biggest galaxies in the universe are, or apart from the CD galaxies, are these giant elliptical galaxies. Uh, they host very massive black holes as well. Uh, they can be as big as tens of kiloparsecs. So not very big, but they are very massive. They can be 100 times more massive than our Milky Way in terms of stellar mass and also black hole mass. And also the dynamical mass, which is dominated by dark matter. Right? So they reside in more massive halos. Right. So in elliptical galaxies, the orbit of stars are random. They are not organized nicely in form of circular orbits in a regular plane. They have random orbits in all directions. Angular momenta are in all directions. So you can actually classify what is the fraction of kinetic energy in rotation versus random motions. So the energy in random motions is much larger for elliptical galaxies. So we mentioned giant ellipticals. Then there are things called compact ellipticals. Compact ellipticals are, as the name suggests, they're more compact. Compact means smaller size. Okay, so this is where the size comes in. So the compact ellipticals are smaller. They're also rarer. They also have somewhat more rotation. Okay. And elliptical galaxies are actually very complicated, as Guru would tell you, because he's sort of working on these certain class of these kind of things. And it consists of various non-obvious patterns. Okay? And there are different, they appear very differently. If you look at their distribution in luminosity, compactness, size, and surface brightness. Okay, so let me actually quickly go to something that I have later just to make this point. Okay, so the book has actually very nice figures and tables. I encourage you to actually go through all of them. And the captions are pretty good as well. You don't have to read the whole material in order to appreciate what's going on. So for example, this is what I was saying. Central V band brightness, IV0. So if you plot surface brightness of a galaxy as a function of radius or angle, it has a maximum value at the center that is plotted here as a function of absolute B band magnitude MB. Absolute magnitude is like luminosity. So the x-axis here is luminosity. This is peak brightness at the center. And these are elliptical galaxies, the normal elliptical galaxies. You see, they are bright. They have very negative values of absolute magnitude. Uh, this M32 is this compact elliptical galaxy that I mentioned. So this is also an elliptical galaxy. Then there are these dwarf spheroidals. They are less luminous. Their absolute magnitudes are higher, so they're less luminous, and their central brightness is also low. So they're very diffuse. It's very difficult to be able to observe these dwarf spheroidals. These U's indicated here are ultra compact dwarfs. They are extremely small. They're also dwarfs. They have low luminosity. Luminosity and mass are sort of one-to-one functions of each other. Low luminosity corresponds to lower mass of stars. Okay, in general. These are globular clusters. Globular clusters, we have actually encountered them. Globular clusters are these spherical distribution of stars, which actually look like elliptical galaxies. Like they look like those E0 class, right? Why aren't they called galaxies? Because they are actually quite different from elliptical. So if you put them in this graph, they have similar central brightness as ellipticals, right? But their masses are extremely small. Right? They are here, whereas these guys are here. So a value of a gap of 5 here in absolute magnitude is a factor of 100 in luminosity. Right? It's minus 2.5 log luminosity. So they are like extremely dim compared to the elliptical galaxies. That's why globulars are different things, although they have the same surface brightness value, core surface brightness value. They are different systems. So you can actually see these, aggregation of these different objects in different places of this phase space. Okay, so this is central brightness versus luminosity. This is the size of the core, right? The central portion, how big is it on the y-axis, and the luminosity on the right. So of course the x-axis remains the same in these two. So these guys were on the rightmost part, so they will still remain on the rightmost part of the figure. Their core sizes are actually big. Right? The more luminous normal elliptical galaxies are bigger, right? Because this is sort of the pattern. These are our globulars. So the size of globular clusters, their core sizes are smaller than elliptical galaxies, but their central brightness is about the same. So their low luminosity divided by small area gives you about the same central brightness. And these are these central brightness is, we'll actually come to something called surface brightness. Central brightness is how bright is the center. So flux divided by angle squared. So flux per unit solid angle is brightness, right? So we'll actually not just compactness. It's a combination of flux and compactness. So if it is more compact, then its solid angle will be smaller. So we'll actually come to that. But anyway, right now I just wanted to show these things that even though they all sort of look elliptical-like, they are very different systems. Okay, we go back to where we were. which is here, here. And these CD galaxies are called lenticular galaxies. These are like mix of massive elliptical and big disks with no clear spiral arms. So there are dwarf ellipticals. This is a dwarf elliptical. This is a compact elliptical. Compact elliptical surprisingly has more rotation. So it's the fact that it appears round doesn't mean that it cannot have rotation. So these are dwarf ellipticals and these are dwarf spheroids. Dwarf spheroids are even more diffuse. They're extremely difficult to find. Like a lot of satellite galaxies of Milky Way have been found, and some of these dwarf spheroids are so difficult to find that they have only been found in the last 2 decades or something. So even with all this sophisticated ability to observe, because they almost look like there's nothing out there. Okay, so here are some examples from the book. Actually, this is a giant elliptical galaxy. Fortunately, this does not give you a size, but as I said, these are like tens of kpc. Giant ellipticals are the biggest elliptical galaxies, and the central part is extremely bright and overexposed in this image. This is a dwarf elliptical, less massive, and you can see that it's not as centrally concentrated as the galaxy on the left. So this is brightness distribution. And here, all these things here, this diffuse thing, this diffuse thing, this are globular clusters. All massive galaxies have globular clusters spherically distributed around them. And some of these guys are perhaps stars from our Milky Way. These things, unlike these things, which are globular clusters. So you have to like look at these things in order to tell these things apart. So it sort of takes quite a bit of experience. So these are just sort of examples of these galaxies that we talked about. So these are ellipticals. This is this lenticular galaxy, S0 kind. In fact, this one has a little appearance of something which looks like a bar. So it's SB0. It has a central part which is elliptical looking and an outer part which is disky looking. So for example, I am not at all good at, if you give me a galaxy image and say, oh, which galaxy is this, I really will have tough time to tell. Because it really takes, you have to look at all these and look at how these different things have been done. But this is a task in which machine learning is very good. So a lot of this can actually be automated now. Okay, so we talked about ellipticals and spirals, but there are also other kinds of galaxies like Large Magellanic Cloud, the LMC, one of our nearest galaxies, Large Magellanic Cloud. It is something called, it's sort of an irregular galaxy, but classified as S. I don't know. I don't think this is LMC, but it is something like a Large Magellanic Cloud. So it is NGC 4449. So it's an irregular, or SBM. So spiral, barred, M here stands for Magellanic type, right? Like our LMC. So you see, it does not really have a very well-defined spiral arm. It does have some tendency towards that. And you see these like clusters of stars. These are young stars which have formed recently. So these are like totally unrelaxed systems. They have very young, massive stars in these regions.
possibly right after a merger?
It can actually be right after it has had a starburst event, perhaps due to a merger or by some sort of a interaction uh, with a nearby galaxy. And these are like star clusters. These things are young stars which have just formed very recently due to these interactions. This is our our nearest large neighbor, Andromeda, or M31. What are these M? There is M31, 32, right? So this is the famous catalog by someone called Messier, who was interested in putting together the comets and stuff. So everything which looked like comet, he classified them, but these things are not comets because they appear every day, right? So comets are things which move fast. So you want to get rid of things which are there but are not comets. So he just classified around 100 objects, which a lot of them were nearby galaxies, star clusters within Milky Way, and so on. So this is M31 or Andromeda. This M32 here is a compact elliptical. I mentioned there are things called compact ellipticals which have some rotation. They are rare galaxies. This is a dwarf elliptical here. So, I mean, as I said, it's very difficult for me to tell that which galaxy type is this or something else, but that's what the caption here says. And the orientation of this is somewhat different. Normally, the north is up and east is down. If you look at the night sky, right, the direction towards the pole star is north. So it's sort of oriented such, it's not oriented the usual way. Okay. The other thing is, even if you see things which are drawn like north is up style, what you will see is that east is not on the left. In the astronomical images, east is on the left actually, not on the right. In geographical maps, right? If north is up, east is on right, right? So Kashmir is on the north and Bengal is on the right. But in astronomical images, north is up and east is on the left, and that's because you're sort of seeing it from top, if you versus seeing it from bottom, right? The east and west switch. If you have the same object, and if you are seeing from bottom versus from top, so the maps you're seeing from top, the sky you're seeing from bottom. So you'll see this and will wonder why is this, but this is sort of the reason. Okay.
So those two are satellites to Andromeda.
Yes, those are galaxies around Andromeda, just like we have LMC and SMC and stuff. Yep, that's correct. So, right. So this is something called Hubble Deep Field, where the Hubble Space Telescope has stared at a blank sky for a long, long time, and what you see are a lot of galaxies. Now, this is a region which appears very populated. This is a region which appears empty, and the exposure is the same. So what you would guess is there are many more galaxies here, less. And if you zoom in and look for longer and more carefully, you see here there are a lot of galaxies in the same area on the sky. Here there are less. What else do you notice? Is there a difference between the color of these and these galaxies? And morphology? Are these? Yes, on the right you have more spirals, on the left you have more ellipticals. So in crowded regions, elliptical galaxies are more predominant in crowded regions, like clusters and groups of galaxies. Whereas spiral galaxies are more common in field environments. So this is a field. Field basically means not a cluster or a group member, and a cluster means like a self-gravitating agglomeration of galaxies, right? And this happens because of multiple regions, mergers between galaxies, something called quenching due to the dense gas, and tidal interactions between galaxies, and so on. Right, there's this NED, NASA Extragalactic Database. If you have any, like, what is NGC 4533? You just put it there and it will give you all the information, papers, and so on. So this is a good, like nowadays, there are so many nice web pages where you can actually just find out things from. So I encourage you to check this out. Okay, so now we'll actually come to this idea of surface brightness. Okay, so we were talking about surface brightness, but I didn't quite define what I mean by surface brightness. So so let's see. So this intensity I, or surface brightness, is defined as flux per unit angular area in the sky. So this is the definition. So this is surface brightness or intensity. F is the flux. Okay, and alpha is this angle, alpha. So you have an object here of size d. So you can actually imagine this as a square of d by d, right? So you have an object of size d, which is at a distance of small d, and it subtends a very small angle alpha. This is the definition of surface brightness, flux per unit angular area. So what is flux? Flux is nothing but L divided by 4 pi d squared, where d is the distance to this object. Flux is energy received by, say, some telescope on Earth, for example, per unit time, per unit area of that telescope. If you take a bigger telescope, you'll receive more energy, but when you divide by the area of your detector, it's the flux. Okay. So this is L by 4 pi d squared, that's F. And then this angle alpha is just capital D by small d. And then you just square it. That's the area, angular area. So this is the definition of surface brightness. And you can see that this D, which comes from the flux expression, and this D, which comes from the angle expression, they just cancel out, right? And you get this surface brightness is nothing but luminosity divided by 4 pi d squared, where d is the size of this, this galaxy. D is the length dimension of this galaxy. So you see, luminosity is an intrinsic property of an emitter, right? If you put it far away or nearby, its luminosity is the same. Its flux changes, right? If you put something close to you, its flux will be much larger. But then the angle subtended by it will also be, if you put it closer to you, the angle alpha will also be larger, right? So this ratio of flux to the angle squared remains a constant. So surface brightness is something like luminosity, which does not depend on how far you place the object. It's an intrinsic property of a source of light. Okay.
Is this the same as central brightness?
Yes, exactly. This is the same as that I showed, or this central brightness that I mentioned. If this depended on the distance, then I would have had to tell you that this is at this distance. This is something which is independent of distance. As long as we are talking about things which are not at redshift of order 1 or higher. When you go to very far distances, the expression for flux is not just L by 4 pi d squared. This d and this d become different when you go to redshift of order 1 or higher. This d is something called a luminosity distance, right? So luminosity by 4 pi dl squared is the flux that you measure. And this d that you have here is something called angular diameter distance. Okay, they are the same in the nearby regions, when you can use Euclidean geometry. But if your cosmological distances, these d's are different. Okay, in fact, this whole surface brightness goes as 1 plus z to the 4. Uh, uh, Actually, surface brightness decreases by 1 plus z to the 4. Basically, if you put these galaxies very far away, their surface brightness dims extremely by an extreme amount at higher redshifts. So it's very difficult to detect galaxies at high redshift because of that. But we are not going to talk about that. But it's good to be aware. Yes.
You can understand that the surface brightness it's like kind of the increase.
Yes.
Not change.
Yes.
But from L by 4 of D square.
Yes.
Can we understand this because luminosity is not changing for an object?
Absolutely. L does not change. D is the size of the object, which is also an intrinsic property of the object. If you take this book and place it anywhere, its size remains the same, right? So D is also an intrinsic property. L is an intrinsic property. So the ratio is an intrinsic property. Right. So this is a physicist unit. So a physicist unit would be in terms of solar luminosity per parsec squared. But unfortunately, in astronomy, this magnitude system comes and makes it extremely scary looking at the beginning. Like so the standard unit in astronomy text that you find for use for surface brightness is this mu, which has units of magnitude per arc second squared. Okay, so magnitude per arc second squared is a unit for surface brightness, and this, of course, is also independent of the distance at which you put the emitter. So the way to think of it is this mu is the apparent magnitude of a star. So apparent magnitude of a star with flux equal to that emitted by 1 arc second by 1 arc second of galaxy. So you take a galaxy with a given mu. So this mu, if you take a star with the same apparent magnitude and spread that light over an area of 1 arc second by 1 arc second, so that surface brightness is equal to this in magnitude per arc second square. So we'll actually try to get a little feel for this when I sort of write some. So it's good to remember that mu of 27 magnitude per arc second squared, it corresponds to 1 solar luminosity per parsec square. Okay, and we'll actually see how. Okay, and I'm gonna do some writing if it allows me to. Okay, so this is where we have something called class notebook. This is where I'm actually this one. So lecture 4, Jan 16. So let's deal with surface brightness. Yeah, you have to become comfortable with magnitudes. There is no way out of it. Okay, because all the papers, everything will use these. But if you spend a day mastering all this, it will stay there with you forever. You'll not face that mental barrier which a lot of people face, not being aware of this. Okay. So let's see. We want to know what is 1 L sun per parsec squared. This surface brightness, if we want to express in terms of arcs magnitude per arc sec squared. Okay, so what do? You take this object of size 1 parsec, and you give it, you spread that light 1 Lsan, that luminosity, over 1 parsec by 1 parsec. Okay, and this whole thing is uniformly lit, and it has it has this much light. Okay, right, and this subtends an angle of 1 arcsec, right? So what did we say? It's the apparent magnitude of a star which has the same amount of light and which is placed at a distance where it subtends 1 arcsecond. So this angle is let's say alpha is equal to 1 arcsecond. So this distance, how much is this distance? Let's call it small d. So this alpha times d is equal to 1 parsec, and alpha is 1 arcsecond, so d is equal to 1 parsec by 1 arcsecond. And you remember your definition of parsec. So a parsec is this. So let's see, 1 parsec is equal to 1 AU divided by 1 arcsecond. Right. This is the definition of a parsec. So and 1 arcsecond is equal to pi by 648,000 radians. I mean, this is pi divided by 180 times 3600. Okay. So what will be the flux of this object? So the flux of this object would be luminosity of this object divided by 4 pi d squared, right? Flux would be this, which is equal to the solar flux, the flux due to the sun at Earth. So
4 by 1 parsec, that D, the capital D.
Can you?
The D.
This D is this, and which is the same as this, yes. Right. So what I'm saying is I'm putting this 1 solar luminosity at this distance, which subtends an angle 1 arcsecond. Okay, so that's just so right. So I'll just divide by 1 AU squared and multiply by 1 AU squared. Right. So this part is solar flux, and so we have 1 AU by d squared. This is the flux due to this object, and so this is what this is actually. So 1 parsec is equal to 1 AU by. So 1 parsec itself is 1 AU by 1 arcsecond squared. So you have 1 arcsecond the whole square, right? So, and which is nothing but this. So so 1 AU by D is 1 arcsecond squared, and so 1 AU by D is 1 arcsecond squared. So this is 1 AU by D, 1 arcsecond squared times F naught. So this is the flux that you have, right? And 1 arcsecond squared is in radians is nothing but pi by 648,000 squared F naught. Okay. So what is surface brightness? I equals F by alpha squared, right? And what is alpha? Alpha again is 1 arcsecond, which is equal to pi by, yes, exactly. So in the end, you will get 1 arcsecond to the power of 4.
1 AU by D squared. AU by D means 1 arcsecond squared.
Yes.
So it becomes
To the 4. This one? Yeah. Okay, let's see. This is what you're suggesting. Yes, this is 4. So this will be 4, right? Okay, so intensity is flux by alpha squared. So yeah, so what did I say? The absolute magnitude. So right. The surface brightness in magnitude per arcsecond square is equal to the flux, corresponding to this. Okay, so the small m is the apparent magnitude is equal to minus 2.5 log L by right, let's see, or F by F sun, right? And what is the small m for the sun? Its value is minus 26 or minus 27. Okay. So basically, this when you put F equals F sun, you get minus 26. Okay. So now we just have to just plug this F value here, and what we get is minus 2.5 times 4 times log of pi by this guy. Okay, and minus 26. So if you do this, this is just 10. This is a log of something less than 1 is negative. So what if you plug all that in, you will get something which is 27. Okay, so 27 or 26 point something. Okay, so 27 magnitude per arcsec square. So this is mu. So 1 solar luminosity per parsec squared is equivalent to 27 magnitude per arcsec square. Okay, so it's sort of easy. It's just sort of a bookkeeping, and you get this 1 arcsecond to the power of 4, essentially. Okay, yeah, but so it's a good idea to actually remember these two things. This is a useful formula, and this 26, don't take this minus 26 very seriously. It depends on the band that you're using, and it depends on it's also not a precise value. It's something minus 26.7 or something, but I'm just sort of illustrating the idea. The other thing that you want to remember is the absolute magnitude is, what is absolute magnitude? Absolute magnitude is a measure of luminosity. So so the definition of absolute magnitude is it is equal to the apparent magnitude if you place that object at 10 parsec away. So if you take our sun and put it at 10 parsec distance, its flux that you receive then is its absolute magnitude. So since you're putting all these guys at the same distance, their apparent magnitude is independent of distance because your distance is fixed now. So the so then this becomes 2 minus 2.5 log L by L sun. And what is the absolute magnitude of the sun? It's about 4.8 plus 4.8. Okay, so if you put L equals L sun, the absolute magnitude is 4.8. If you're like, and this is the other formula that you. So capital M is absolute magnitude, which is a proxy for luminosity. Small m is apparent magnitude, which is a proxy for flux. You know, these you have to just. These are the forms which are easiest to sort of keep track of. If you're using this for your research paper or something, you just have to look at more precise values. Okay. Good. Yes. That's not distance. That's the size. The size squared. Yeah.
That size of measuring in parsec.
Yeah. So if you express it in terms of L sun by parsec squared, then you're using the units to measure that area in parsecs. Oh no! It's not. This is not mag by parsec squared. It's mag per arc second squared. Right. Okay. Okay. Let's go back to our slides. I mean, last time when I was actually doing it, it just took me forever to derive it. I mean, I understand it, but you know, just this magnitude and apparent magnitude is extremely annoying, actually. Okay, so you know, keep this in mind. One else. Exactly. This. So. So what would. So yeah, exactly. So this surface brightness, the galaxies do not like abruptly end, unlike stars. Stars, you know, they have a surface and then outside it there's zero density. But galaxies just go on and on and on forever. So when do you say that the galaxy has ended? When the surface brightness decreases below some threshold, is as Guru was saying that this ICL, what is the value threshold value that they 26.5. That's yeah. So there are like these standard values for surface brightness that are used as like the size of a galaxy. Okay, so for example, the centers of like elliptical galaxies can have a high surface brightness as 18 magnitude per arc second squared, right? That was 27. One L sun by parsec squared was 27. What I'm saying is the centers can have as high as 17 or 18. That's like 10 difference in magnitude. That would be like 4 orders in flux. So the center is 4 orders of magnitude brighter than the edges of these galaxies, essentially. And of course the elliptical galaxies are brighter in the red or infrared bands compared to the blue bands. So brighter means lower value of surface brightness. Like in our band, it can be like 16 instead of 17 or 18 magnitude per arc second squared. 16 is smaller, but it corresponds to larger surface brightness. You know, this magnitude system is you have to be extremely careful, especially about this, that a larger value corresponds to smaller luminosity or flux or surface brightness. And there are also signs because it's a logarithmic unit. So sometimes people actually also use R25 as the radius of a galaxy. R25 is the radius at which the surface brightness contour takes a value of 25 magnitude per arcsecond square. Or there is something called Holmberg radius, which is 26.5 magnitude per. All these are like traditional things. Okay. So 27 is actually pretty dim. It's 1 solar luminosity per parsec squared. So what would be the surface brightness at the location of the sun? Let's see if we can estimate it. So at the location of the sun, let's say all stars are like sun, like the sun. Okay. So and we just sort of talked that the distance between the stars is about a parsec, right? So the volume luminosity density is L sun per parsec cube. What we want is surface density of light, which would be, you have to multiply it by the scale height so that you get a luminosity per unit area. So the scale height is like, say, 100 parsec. Okay, so 1 L sun per parsec squared times the height, say 100 parsec. So it becomes 100 times larger than this 27, this 1 L sun per parsec squared. So 100 times larger luminosity means by how much larger is the magnitude? 5. Correct. So a factor of 10 in luminosity corresponds to 2.5 in magnitude. So 100 would correspond to 5. So 27 minus 5 is 22. So the rough estimate for the surface brightness in the solar neighborhood would be about 22 magnitudes per arcsec squared. So be a little comfortable with all these things. See, these are not extremely accurate estimates, but they will not be off by more than an order of magnitude. So it's important to actually be able to do these things quickly and get a feel for these, rather than just being obsessed about the second decimal place right at the beginning. You want to do that later on, but quickly get a feel for all these things. Okay. So for example, this is Andromeda, I believe. So you can actually see what is the surface brightness of this patch on this galaxy. You just measure the flux coming from here, divide by the angle subtended by this squared. That's the definition. Okay, and that is related to the amount of light this guy is emitting divided by its area, 4 pi d squared. So they are equivalent definitions.
What is the average angular distribution of a galaxy? How big is a galaxy generally when we see it?
Oh, it depends on how close it is. Like Andromeda is like huge. Like our Milky Way is huge on the sky. Let's say if you
Milky Way is all around, so 180 degrees.
I mean, yeah, you can say that, yes.
What about let's say an average distance?
So you take an average size of a galaxy, let's say 10 kpc or 20 kpc diameter, and if you put it at a megaparsec, you can find the angle, right? So Andromeda, 20 kpc divided by a megaparsec, that's sort of a big angle actually. Like the moon and the sun are half a degree. So this thing is actually much bigger than that. This would be much bigger than that. So they're like diffuse big guys. Okay. So how do you measure the surface brightness of a galaxy? You just sort of take, you take a telescope, you have a CCD, you expose this area that you're trying to image for a long time, and it will just register, photons coming from each of these positions and make a nice map of the galaxy. But that's not how things actually normally work, because there is this atmosphere that we are surrounded by, and the atmosphere emits it emits light in optical and in infrared, especially in infrared. All these molecules like water vapor and so on emit in infrared. There's also like a, the general black body, the Earth, we sometimes take it as a black body. It sort of re-irradiates the radiation received from the sun. So all that makes it very hard for us to detect these very diffuse things like outskirts of galaxies. Okay, so here is actually a table from the textbook, and these are the bands. So U, B, V, R, I. So this is close to ultraviolet, blue, visible, red. This is infrared, J, H, K, L, M. These bands. Okay, and so these are the central wavelengths of these bands. This is if you have a full moon night. Okay, so this is the sky brightness. The atmosphere itself will have this big of brightness. So how can you measure like 25 if the sky itself is 19 magnitude per arc second squared, and if you're sort of trying to look at the edges of the galaxies, which are 25 magnitude per arc second squared, which is like a factor of 100 lower in brightness, how would you do that? There's a problem. So you don't want to observe galaxies on full moon. You go to dark nights when there is no moon in the sky. Then these things become better. Right? These numbers become higher. That is, your limit becomes better. You can go to much lower surface brightness. And if you go to space, these numbers become even better. So this is in magnitude per arc second squared. This is the same quantity. So the same quantity expressed in slightly in different units. So this is micro Jansky per arc second squared. So Jansky is a unit for flux density. So flux per unit wavelength. Right? So amount of energy received by a telescope per unit area, per unit time, per unit wavelength. That's Jansky. And 1 Jansky is 10 to the minus 26 in MKS units, and minus 23 in CGS units. So just so these are more more physics units. These are the astronomy units. These are conversions between them. The other good place to go observe is the South Pole. Now, but look, this is not comparable to space. Look at space is so much better, so much lower values compared to even the South Pole. Right? So you want to send our HSTs and JWSTs into space, even though their diameter is JWST is 6 meter, right? But the ground-based telescopes are already 10 meter, and we are going to 30 meter. But space has huge advantages, right? The other thing is all these numbers, you see, these are still not going to 23. What do you do? I mean, if you want to go to 25, 27 magnitude per arc second squared, how do you do it? What you do is you look at a patch in the sky, okay, and you measure this. The central part will be standing out, right? It is 17 or 18. That will be standing out. Then you go farther and farther out. You are dominated by the sky. Okay, you take your data, but then you look at slightly different region of the sky. That will give you the ambient value. Okay, so then subtract one out of the other. So there will be so much slightly higher light that would be coming from close to the galaxy compared to the empty region away from the galaxy, and then you subtract the two, and that's how you can actually get values which are below the value of brightness of the sky. Okay. So this is a good metric to keep in mind. What is the surface brightness limit of my telescope at a particular site. That's, if your limit is better than something, only then you can recover your surface brightness profiles. Yes.
Times we measure flux per unit wavelength of per unit. But here we are not doing.
We are not. Yeah. Right. It really depends on what you're after. Suppose you're after measuring the spectrum of an object, then you have to do per unit frequency or per unit wavelength. If you're not so much after measuring the spectrum, you just want to get maximum amount of light, you just want to do photometry. Photometry is you have a broad band and you're just making images. For the morphological classification of galaxies, all you need is photometry. You're not doing spectra. Then you just integrate over the whole band, the lambda or the frequency band. So this is an example of sky photons. So number of photons per unit time, per unit lambda, per unit per unit angle squared. And you see all these things. These are emission lines of your water, CO2, and all these molecules. And on top of this, you have this black body. You see the underlying black body there, the Planck spectrum. That's just the like 300 Kelvin black body, which corresponds to the sort of the temperature of the atmosphere. And you see these KLMN bands. So this is 2 microns. So this is like infrared, right? So this is near infrared. And you have these windows where you have somewhat less sky emission. So your observational bands are located in these zones where there is less sky emission, so that it's easy to subtract out the sky. And if you zoom in on this region, for example, from this 1.5 to 1.6 micron, this is how these things look like. They're extremely complicated, this emission from molecules. And this is at Mauna Kea, Hawaii, which is the best place, among the best places on the earth to do these kinds of observations. So even there, things are tricky. So yeah, these are the closely spaced emission lines. Okay, so this was about the surface brightness of galaxies. What about, so we had talked about this something called initial mass function or mass function of stars. How are the number of stars, what is the number of stars between, say, mass m to m plus dm or luminosity L to L plus dl? We have encountered those kind of things. Can we do a similar counting of galaxies, right? How many galaxies are there per unit volume of the universe which have, say, luminosity between L and L plus dl? That quantity is called the galaxy luminosity function. Okay, and it is sometimes denoted as phi. So this is number of galaxies per unit magnitude per unit volume. So if you look at 10 megaparsec by 10 megaparsec by 10 megaparsec cube in our neighborhood, and count the number of galaxies which lie between the magnitude value, absolute magnitude value, you make bins in these absolute magnitude values and just sort of put how the numbers there in that bins. So this is the kind of data that you will get. This is blue star forming galaxies. This is, this exercise done for only blue star forming galaxies. This is what you'll get, these stars. If you do the same exercise for red old stars, red stars which contain red old stars, galaxies which contain red old stars, you will get something like this. Thing to note, we already talked about it, that the most massive galaxies are the elliptical galaxies, which are red and dead most of the time. And at lower masses, you have blue star-forming galaxy spirals dominating. You see that. And if you don't distinguish between blue and red, this is, if you sum them up, this is what you get. Okay. This is the galaxy luminosity function. Okay. This is actually very commonly used in galaxy studies. And it has a very characteristic shape. Okay. So this is the data. This is a fit to the data of this kind. This fit is described by something called a Schechter function. This is the functional form of that function, Schechter function. So it is a power law with an exponential cutoff at large luminosities. So you have a large number of small galaxies with small luminosities. And as you go to larger and larger luminosities, their numbers drop exponentially. You don't have, the very, very luminous galaxies are extremely rare. They are exponentially rare. Okay, this is what it says. Okay, yeah, I'll talk. So the caption is actually here. It actually describes that dash line too. So this is the number distribution. One can actually also do a luminosity distribution, right? That would be nothing but, so the luminosity between L and L plus DL would be L times phi delta L. So if you multiply this solid line by L, this is how it looks like. In fact, the y-axis is the number per unit volume per magnitude here. So this is the y-axis for these data. There is this luminosity per unit volume per magnitude on the right. The unit on the right is this, and this corresponds to this guy, this dash line. They are related because luminosity coming from L to L plus DL is nothing but the mass coming from that and the luminosity of that particular mass bin. You just multiply this by L and you get the thing on the right. So the thing to note is that most of the light is actually dominated by L star galaxies. You can see if you just sort of take equal sized bins here. So this is a log plot. Log numbers, log luminosity. If you see that the area under the curve for this dashed curve is dominated around L star. L star is this cutoff where the exponential takes over, whereas the numbers are dominated by low mass guys. And I said that mass and luminosity are sort of, not linearly proportional, but proportional to each other. So most mass and most light in galaxies is around L star galaxies, and our Milky Way happens to be an L star galaxy. So most of the mass and light in the galaxies around us are in the, just open and close that once. Okay. I just open that door. Yes. And you can do this exercise in different bands and so on. So this is like an industry. People have collected millions, hundreds of millions of these galaxies and done this exercise. And it's actually a very important exercise because all this, the abundance of galaxies of different masses tells us about how these galaxies form, right? So here is why a galaxy mass function is important. So this blue thing is a schematic representation of galaxy luminosity function. Okay, so it sort of more or less looks like what we have here, sort of flattish part and then an exponential cutoff, this blue stuff. Now, we can also, so if you do the theory of structure formation in the universe, Or if you look at n-body simulations which simulate dark matter, which is the dominant mass component in the universe, and if you just calculate the number of halos as a function of their mass. So this red curve here, which is sort of called theory here, is done for halos in, say, cosmological simulation. What you see is that this has a somewhat different shape than this. Okay, the shapes are important. The y-axis has been normalized so that they overlap in this L star region. What you see here is that the number of galaxies hosted by halos at low mass is smaller, and so is the number of galaxies at luminosities or masses much greater than L star. So the star formation efficiency of galaxies is suppressed both at low masses and at high masses. Okay, and this leads to something called feedback. Feedback is the process of energy injection by supernovae and by AGN, these massive, supermassive accreting black holes, which prevent star formation in their halos. So this luminosity, putting together this luminosity function, allows us to do this exercise of like connecting these observations with theoretical understanding of galaxy formation. Okay, so I think we are already at the end of the class. I'm gonna end here, and we'll meet next time. So next time we'll start with elliptical galaxies. Okay.